Hello, you guys. Welcome back to another video. Today we're going to be talking about properties of functions. As you can see on the screen, there are three different things we're going to be talking about at the beginning, which is increasing, decreasing, and constant. When you guys are doing this, make sure that you're reading the graphs from left to right. That's going to be very, very important. I'll write it here so that you don't forget. Read graphs from left to right. Okay, and excuse the noise in the background. They're doing construction next door or something, and it's really loud, so I'm sorry. All right, so from left to right, we'll start off with increasing. What that means is if you can draw the graph without having to lift your pencil and you see your pencil going in an upwards motion, then that would be increasing, okay? So from left to right, I'm going to start, and then notice that I'm going up. So that would be an example of increasing. Okay, decreasing is the same thing. You start from the left-hand side, and if you see your pencil going in a downwards motion, then that would be decreasing. Okay, and then constant is if it doesn't go up or down, and it just stays at the same spot forever. That's a constant graph. Okay, so there's a word right there called extrema. What extrema are, that's a vocabulary word. They're the points in the graph where the direction changes. Okay, and that has to be either from increasing to decreasing or decreasing to increasing. So it has to be one of those two. I'm going to abbreviate increasing with INC and decreasing with DEC. Okay, so it has to happen when it's changing directions from increasing to decreasing or decreasing to increasing. Okay, so the first thing I want us to do is draw arrows on all of these graphs because they are missing all of the arrows. Okay, now let's start with the first one. So starting from the left-hand side, you can see that my graph is going up. So this would be increasing. But it doesn't go up forever because then notice that it starts to come back down. So this is where it's decreasing. And then it starts to go back up after, and it changes to increasing again. Okay, now notice that when there's a change in direction, there's a little overlap in color right there. So where it changes from increasing to decreasing or decreasing to increasing, that is where you're going to have extrema, okay? So these 2 points right here will be a type of extrema. Now there are two different types of extrema. There's maximums and minimums, okay? So there's the little hills and the valleys that you get when you're drawing your graph, okay? So again, the little hills or the little valleys. So this will be a type of maximum because at the top, and this one that's at the bottom will be a type of minimum. Now there are two different types of maximums and minimums. There are local maximums and minimums and absolute. Okay, another word for local is relative, and they might use these two words interchangeably on the ACP, so make sure you are familiar with both. So local is relative, and absolute is the same thing as global. Okay, those words will also be used interchangeably on the ACP. Okay, so now what's the difference between local and absolute? So absolute, think of it as the absolute highest or absolute lowest point in the graph. And if you were to draw a line through it, the point, there would be nothing above it or nothing below it. Okay, so let's observe this one. These arrows right here indicate that the graph is going up and down towards negative and positive infinity, right? This line goes up forever and this line goes down forever. Okay, so notice that these points that we had identified earlier, they are in the middle of the graph. So if I were to draw a horizontal line through this maximum, okay, notice that there's stuff above it. Okay, so because it's not the absolute highest point in the graph, this maximum has to be a local max. So local maximums and minimums are basically in the middle of the graph, and then the absolute are the absolute like extremities of the graph. Okay, so let's do the same thing for the minimum. So again, remember this line goes down forever, and if I were to draw a horizontal line along the minimum that we have right here, notice that we have all of this still existing below it, meaning that that point is not the absolute lowest point, making it just a local minimum. Okay, so we have a local minimum and a local maximum right there. Now, the absolute maximums and minimums only occur if it doesn't go to infinity. So right here, because these two arrows indicate negative and positive infinity, there will not be an absolute maximum or minimum. Let me make a note of that here somewhere in the corner of your paper. Okay, if your graph goes to negative infinity, we'll say there's no absolute minimum. Okay, if it goes to positive infinity, there is no absolute max. Okay, so again, for these two, for this one graph, there is no absolute minimum and no absolute maximum. Okay, and then don't forget that another word for local is relative. So I could say local slash relative maximum. And the same for down here, I could say local slash relative minimum because they mean the same thing. So if I were to ask you where's the relative minimum, you need to know that that's the same thing as local. Okay, there's that. Let's do another example. So you always start from the left-hand side. So from the left-hand side, notice that my pen is going down, but then it transitions and moves up. Okay, so it goes from decreasing to increasing. And then remember, when there's a change in direction from decreasing to increasing, that creates a type of extrema in the graph. So right here where it changed, this is going to be a minimum. Now, what type of minimum? So again, you can do your little horizontal test, horizontal line. If you draw a horizontal line, you can observe that there is nothing below this. It is completely empty. So for that reason, this point will be the absolute lowest point or the global minimum. Okay, so absolute or global minimum happening right there. And then these two arrows going up towards infinity make it impossible to have an absolute maximum because it's going to infinity. And we've already talked about that. Let's do the next example. So starting from the left-hand side, notice that my pen has to go upwards, so it's increasing, and then it goes down to decreasing. Okay, and then right here where there's a change in direction, that will be a type of extrema. As you can see here, is going to be a maximum. If you were to draw a horizontal line through the point, and you can just grab the edge of your paper, the edge of your pencil, the edge of your ID badge, whatever you have on you, and then just observe, notice that there's nothing up here. So this would have to be the absolute highest point of the graph. So this will be the absolute max or the global maximum. Okay. No absolute minimum because these arrows are going down towards infinity. Okay. Here I have a note that the X values tell you where you are increasing and decreasing. So when I'm asking you about the intervals of increasing, decreasing, you will only be focused on the X values, and we'll practice that on the next page. Okay. Here we have some more examples. I want you to again add the arrows. They are missing. Okay, so let's start with the first one. So notice that my pen has to go down. You always start from the left-hand side. It goes down, then up, then down again, and then up again. Okay, now I'm going to start abbreviating, increasing with INC and decreasing with DEC. Okay, And anytime there is a change in direction, you will have the extrema. So right here, and right here. Okay, so now let's try to identify what type of extrema it is. Okay, so we know that these two down here are going to be some type of minimum. This one and this one are a type of minimum. This one has to be a type of maximum. We got to figure out what type. Okay, so starting with the first one, if you draw a horizontal line, let me zoom out a little bit. A horizontal line through that minimum, observe that there's nothing below this graph. And this is a different graph, so don't worry about this one. There is nothing below that minimum, so this one has to be an absolute minimum. And I'm going to abbreviate absolute with ABS. Okay, so that's an absolute minimum, which is different than the other minimum that we have. So if you were to draw a horizontal line through this minimum here, this one, you can see that there is graph below it. So since there's this down here, this one is not the absolute lowest, so this one here has to be the local minimum or the relative minimum. Okay, now the middle one, we said it was a maximum. If you were to draw a horizontal line through that, you can see we have a lot of graph. This one goes up forever, this one goes up forever. So this point right here is not the absolute highest, but it is a type of maximum. It will just be local or relative maximum. Okay, and again, if your graph goes to infinity, there is no absolute maximum. Okay, just a local max. Okie doke, let's try another example. Let's do this one over here. So when you're starting off on the left-hand side, my pen has to go down, but then it changes to increasing, then it goes back down to decreasing. Okay. My letters look so ugly, I apologize. Okay, anytime there's a change in direction, here and here, we have an extrema. So this has to be a minimum, the other one has to be a maximum. Okay, but notice that these go up and down forever, right? So this one, when it goes up to positive infinity, there's no absolute max. And when it goes down to negative infinity, there's no absolute minimum. So if there's no absolute, these other ones by default have to be local or relative maximums and minimums. Okay, and if you were again to do the same little horizontal test, you can see we have more stuff up here. If you were to check this one, you see we have more stuff down here, so they have to be local maximums and minimums. Okay, the one in the center, starting from the left-hand side, my pen goes up, and it keeps going up, and it keeps going up. So it actually goes up forever. It kind of appears to some that it's constant in the center, but notice that if I were to draw a horizontal line through it, it's actually not that it's not constant. Okay, because it kind of has a slope right here going up and as well here. Notice that it's going up if you zoom into it. So it's not constant. It looks like it from the naked eye, but it's not constant. So this is increasing all the way up. Now, you're not wrong that there is something happening in that part in the center. What that's called is a point of inflection. So right here, this would be a point of inflection, and I'm going to tell you the definition of that. Basically, what a point of inflection is when the graph changes concavity. From curving down to curving up. Okay, the point of inflection is where the graph changes concavity from curving down to curving up. Now, what does that even mean? Okay, so it's basically about parabolas, the concavity of a parabola. So think of it like a smiley face versus a frowny face. Okay, so you can see that at the beginning of the graph, we had half of the frowny face. We had half of this here. Okay, and then when we got to the point of inflection, we got the other half of the smiley face. Okay, so both of these combined created this whole graph. Okay, so it changed concavity. It was curving down and then it switched to curving up. That's all that means, and when that occurs, that's called a point of inflection. Okay, let's go on to the next page. Okay, we have two more examples. At the bottom, I have some important notes. So endpoints cannot be local extrema. Okay, cannot. However, endpoints can be absolute extrema. So not local, but they can be absolute. And what are endpoints? Endpoints would be this point right here and this point right here. So they're the ends of the graph. Okay, so they can be absolute, but they can never be local. So let's go and label these. Okay, so if I draw a horizontal line here, notice there's nothing below, so this one has to be an absolute minimum. Okay, this one, if I draw a horizontal line, notice that there's stuff above it, so it can't be absolute, so it has to be the local maximum. Okay, we already know there's an absolute minimum, so this one has to be the local minimum. The next one, if I draw a horizontal line, notice there's nothing above it, so this one is the absolute max. Okay, and this one at first glance appears like a local minimum. Okay, but remember that endpoints cannot be local anything. Okay, so if it was a local max or a local minimum, but it's at the end, it can't be anything. So this one I'm actually going to say nothing. And I'm going to point, I'm going to draw an arrow pointing to the explanation. So when you look back at your notes, you understand why it's nothing. Okay, so this one was okay as an endpoint because endpoints can be absolute extrema. Endpoints can be absolute, but endpoints cannot be local. So that's why this one is nothing. Okay, so this one's good, this one is no. Let's do another example. So again, starting off at the first point, if I draw a horizontal line, there's stuff below it, there's stuff above it. So it can't be an absolute minimum, it cannot be an absolute maximum. And because it would have been a local extrema, but notice that it's an endpoint, and endpoints cannot be local extrema, so this one is also nothing. I will also point to the explanation of why it is nothing. Okay, that bottom one is the lowest point of the graph, so this will be the absolute minimum. Okay, sometimes they throw in like random points like this in the middle of the graph to try to throw you off, but remember that extrema only happens when there is a change in direction. So here we went down, and now here we're transitioning up. But within this point, there was no change in direction. It was always going up. Okay, so if it doesn't change directions, this is not a type of extrema. Okay, and at the same time, if the endpoint is open, or not, it doesn't even have to be an endpoint. If it's a point on the graph and it's open, it will not be a type of extrema. Okay, it has to be a defined value, and this one is not defined. So it's nothing, because it's missing the point there. Okay. So now let's practice actually writing the intervals of increasing, decreasing, and constant. So I have two examples here. So I'll start off with highlighting where they're increasing and decreasing and where they're constant. Okay, so always start from the left. My pen goes up, then my pen goes down, then my pen goes up, and then my pen stays constant. Okay, so I'm going to write increasing, decreasing, and I'm going to color code. It helps to color code sometimes. So if you have colors, you can follow along. Okay. And remember in the first page I said you're only going to be using the x values. So from what x value to what x value are we increasing, decreasing, and constant? Okay. So remember that on the left-hand side you have negative infinity. On the right-hand side you have positive infinity. So let's do the pink first. Okay. So from negative infinity to -3, we are increasing. Another point that we're increasing, another pink area, is from 1 to 4. Okay, so from 1 to 4, these x values, we are increasing. And you use the unison symbol just like we do when we're writing the domain to combine those two pieces. Now I'm going to make a note here. You might be wondering why I'm using parentheses when those points are clearly closed. Okay, so I'm going to zoom in to the side, And I'm going to say always in caps because it's really important that you're always going to use parentheses. Never use brackets. Okay, the reason that you're never going to use brackets is because notice at this point at -3, it corresponds to the end of the increasing and the beginning of the decreasing. So because -3 will be associated with both the beginning and the end of a direction, it's going to be part of both intervals, so it's not exclusively applied to one. And since they're going to share that value, it's going to be an open parentheses. Again, because it's going to be shared. Okay, so then notice that when we write decreasing, we're decreasing from -3 to +1. Okay, so within these x values, we are decreasing, going down. Okay, and then where are we constant? You can see from +4 to infinity, we're going to be constant. Okay, so that's the first example. Let's try another one. So we'll start by highlighting where we're increasing, decreasing, and constant. Starting from the left-hand side, my pen goes down. Then there's a vertical asymptote. I pick back up, my pen is still going down. I stop, I start again, my pen is still going down. Okay, so when I write my increasing, decreasing intervals, notice that we don't have pink anywhere. It never increased, so I'm going to put none. And notice we have no orange either because it was never constant, so I'm going to put none. For decreasing, you can't just put -infinity to infinity because we have two vertical asymptotes, so you do have to stop at the vertical asymptotes, okay? So -infinity, that is at -4, that first vertical asymptote, union, -4 to +2, union 2 to +infinity, okay? So from here to here, -infinity to -4, then from -4 to +2, and then from 2 to infinity, okay? Let's try another one. So we'll start by labeling or highlighting, okay? So we start with decreasing, then increasing, then decreasing, then increasing again, okay? So list the intervals where it's increasing, decreasing, and constant. Okay, so I'm still sticking with my color coding. Remember, we're only doing x values, and remember, it's always parentheses. Okay, so I'm increasing. It is pink from -1 to +1. Okay, union, I see another pink area from 3 to infinity. Okay, now where are we decreasing? So we're decreasing from -infinity. Remember, this means -infinity. Please don't say it's like -3. So from -infinity to -1, union, and it's green again from 1 to 3. Okay, and as you can see, it is in orange. It's not constant anywhere. So none for that one. Okay. Now we have to do the extrema. So you see B, C, D, and E are talking about the local maximums and minimums and absolute maximums and minimums. So let's label on the graph first, and then I'm going to show you a different way that we can write the extrema instead of as coordinate points. Okay, so the first one is this one down here. As you can see, it's not the absolute lowest point of the graph. This one looks like it's the absolute lowest. So this one will just have to be a local minimum. Okay, this one, like we just said, this one would have to be the local maximum. Sorry, not local maximum. I meant absolute maximum. And my gosh, I meant absolute minimum. I'm so sorry. Absolute minimum. And then the one at the top would have to be a local maximum. It cannot be absolute because, again, these arrows here indicate that there is no absolute max because it goes to infinity. Okay. So one way that we're going to write this, and when I ask you to write the extrema, this is how I want you to write them, okay? So local maximum, you're going to start with writing the y value first and then specify the x value. So it's going to read like this. So the local maximum was at 1, 2. Okay, so you're going to say of 2 at x equals 1. Okay, because maximum and minimums have to do with the height, right? How high does it go or how low does it go? So it went up 2 units, so it's up here when x is 1. So that's basically all you're going to be doing. Okay, so the local minimum was at -1, +1. So you're going to say local minimum of +1 at x equals -1. Okay, whereas the absolute max, we already said there would be none because it goes to positive infinity. And the absolute minimum, okay, so of 0 at x equals 3. Okay, now I'm going to write something that sounds kind of confusing. Just write it down and I'll explain it in a second. Okay, so not every local max or minimum is an absolute max or minimum or extrema. But every absolute max or minimum is a local max or minimum. Okay, so basically every absolute will also be local, but not every local is absolute. So I have two examples for you, a real life situation and a math situation to kind of help you understand what this is saying, okay? So the first one, think of sweaters, okay? So there are a lot of different types of sweaters. You can have a full zip sweater, you can have a half zip sweater, a quarter zip sweater, a hoodie, you can have a turtleneck sweater, a bunch of different types of sweaters, okay? A crew neck sweater. So I can say every hoodie is a sweater, but not every sweater is a hoodie, right? Every hoodie is a sweater, but not every sweater is a hoodie because there are many types of sweaters, not just hoodies, okay? A math example would be every square is a rectangle, but not every rectangle is a square, right? So the definition of a rectangle is just 4 sides, and a square has 4 sides, so by definition it's a rectangle. But not every rectangle is a square, because for it to be a square, they have to be equal sides, and not every rectangle has equal sides, right? So every square is a rectangle, but not every rectangle is a square. Every hoodie is a sweater, but not every sweater is a hoodie. Every local max is an absolute max, but not every absolute max is a... Did I write that wrong? No, I wrote it right. I just confused myself. Anyways, I hope that makes sense. Um, so basically, this absolute minimum will actually also be categorized. So I'm gonna say and local minimum. So it's actually gonna be both. Okay. Because all an absolute extrema is a point in the graph that's lower than the other minimums or higher than the other maximums. So they're technically all local extrema, just that one point in particular will always be higher than the others and one point will be lower than the others. But they're all local extrema. Those points that are higher or lower are also absolute maximums and minimums. I hope that makes sense. But yes, so this stuff that I wrote for absolute minimum will also apply for local minimum. So I'm going to go ahead and copy this here as well. So we have local minimums of 1 at x equals -1 and also of 0 at x equals 3. Okay, because it applies for both. And I know that sounds kind of confusing if you don't understand it. Usually they won't ask you like that anyway. They'll usually just be very specific, is it absolute or local? But I just wanted to share with you that technically it's both. Okay, moving on to the next page, we have some more examples of extrema. So 0, 1, notice that is the absolute lowest. There's nothing else below here. So this will be an absolute minimum. And remember that you can have absolute extrema as endpoints. So that one is okay. That one's acceptable. I'll move this here so you can read it. Okay. 3, 6. So if you draw the horizontal line, there's nothing above it. So this will be the absolute maximum. Okay. 4, 4 has to be the relative minimum because we already have an absolute minimum, and you can have both. Okay. And then 5, 5, notice that it is neither the highest, it is neither the lowest. So it would be local, but local extrema cannot be extrema. So this one would be nothing. Okay, let's try another one. So 1, 2, if I draw a line, it's not the highest, it's not the lowest, so it's local. Local extrema cannot be extrema, so this one will be nothing. Okay, 3, 1, that one will not be an absolute minimum, okay, because it has a hole. So remember, it has to be a defined value for it to be considered an extrema. And 5, 3 is the absolute maximum because it's the highest point on the graph. Okay, let's try another one. So 1, 4, again, not the highest, not the lowest, it's just in the middle, but it's a endpoint, so it cannot be an extrema. So it's nothing there. The hole, nothing because of the hole. Again, same reason as before, it has to be defined. And then the infinity symbol, remember if it goes to infinity, there's no absolute maximum. So notice this one has literally no type of extrema. This is just nothing there. Let's try the next one. Okay, so if I draw a line through here, notice there's nothing below this, so this has to be the absolute minimum. And it is an endpoint, but endpoints can be absolute extrema, so this one is good. And again, arrow means there's no absolute maximum. Okay, so we're done with that one. Let's move on to a calculator example. You might need to practice this when you go to school. If you're watching this at home, practice with the inspires so you can get the steps down. But I'm going to show you the steps on my calculator. Okay, so I'm going to open up a new graph and I'm going to type x to the power of 4 minus 7x squared plus 6x. Okay, and it looks something like this. Now, you can't see the whole graph, so what you have to do is do menu, zoom, and then zoom out. Mine is a little different because it's on the iPad, so I don't have the zoom out. All I have to do is pinch to go out, but on the calculators, you do menu, zoom, zoom out, and you keep zooming out until you see the bottom of the graph. Okay, so now that I can see the whole graph, I'm gonna go back to my notes and sketch it out. And don't make it really big because we're going to be writing some things on the right hand side. And it's not going to be perfect, but it doesn't have to be. Just a little sketch to get the idea of what the graph looks like. Okay? So where are the extremas, right? Remember that extremas occur when there's a change in direction. So starting from the left-hand side, my graph goes down, then it goes up, then it goes down, then it goes up again. So every time I'm changing colors here from pink to green or vice versa, so here, here, and here, we're gonna have a type of extrema, okay? So notice that on this one, it is the absolute lowest, so this is the absolute minimum. This one has to be the local minimum because there's a lower point in that one. Local maximum. No absolute max because of the arrows going up to infinity. Okay, so let me write all of these down. So absolute maximum, absolute minimum, local maximum, local minimum, and then we're also going to write our increasing, decreasing intervals and the constant. Okay, so let's go to the graph now, and I'm going to show you how to find all of these points So the first one was absolute maximum. We have already said there is none. So let's try to find the absolute minimum, which is this point down here. Okay, so let's go to the graph and you're gonna do menu, analyze, and then you're gonna be specific because notice we have minimum and maximum as options. And so we said we're gonna find the absolute minimum first. So I'm gonna select minimum. Okay, you're gonna have two dashed lines show up on your graph. The first one appears kind of to the left of the graph. What you want to do is kind of drag it to be to the left of the point. Okay, so you don't want to put it literally on the point of the minimum, you want to put it just to the left. So give yourself some space because then a second line appears and it's going to make a shaded area and you're going to drag this line just to the right. So what you want is for your minimum to be in between the shaded areas. You don't want it to be like this, okay? It needs to be in the middle of the gray shaded area. The word minimum should populate, it should just pop up on your graph as well as the actual coordinate point for the minimum, okay? So that's the minimum value right there. So remember when we write extrema, we're going to say of the y value at the x value. So I'm going to say of negative 24.1 at x equals negative 2.06. Okay. Now let's try the local maximum. So we'll go back to the graph, menu, analyze, maximum. So this time we're going to be looking for the local max. So select maximum. Again, drag the dotted line. And this time we're looking for this middle one, okay? So I'm not going to put it right here in the center. I want to put it just to the left, okay? And then a second, after you click, a second line will appear and you want to drag it just to the right. So notice that not too close, but just so that the point is in the shaded area. The word maximum should pop up with the coordinate point that it corresponds to, okay? So remember, of y value at x value. So of 1.32 at x equals 0.46, 456. Okay, let's try the local minimum. Menu, analyze minimum, drag it. You gotta be intentional. You can't start it over here because if not, it'll select this minimum first and you're trying to get this one, okay? So you have to go past, make it just to the left, click just to the right so that the point is in the shaded area. Minimum word comes up and the point comes up. So that's how you can tell if you did it correct, okay? So y of x, so of negative 1.77 at x equals 1.6. Okay. So now how are we going to figure out where it's increasing, decreasing, and constant? What we're going to do is use these x values because remember that these are only x values. So we have the x values of the extrema. We know where we're going to be starting or stopping the intervals, okay? That sounds kind of confusing at first, but let me show you. So the absolute minimum occurred at the x value negative 2.06. The local maximum occurred at x equals 0.456, and the local minimum occurred at x equals 1.6. Okay, so that's going to help us figure out where we're increasing or decreasing because remember the extrema is the change in direction. So we know where the extrema are, we know where one changes direction and the other one begins another direction. Okay, so we'll start with the increasing. So it is pink from negative 2.06 to 0.456. Okay, so from negative 2.06 to 0.456. Okay, and then we're also increasing somewhere else. So from 1.6 to infinity. Now where are we decreasing? So we start decreasing at negative infinity. and it stops decreasing at negative 2.06. And then we decrease again from 0.456 to 1.6. So between these x values, we are decreasing. And as you can see, it's not constant anywhere. So I'm going to put none for that one. Okay, so now you can see how knowing the x values of the extrema can help you determine the increasing, decreasing intervals. Okay, let's try another example. Identify all local extrema and absolute extrema, and if one does not exist, state D and E. Okay, so starting with this one, notice it's not the highest, it's not the lowest, so it's a local maximum or relative maximum. Okay, this one right here, these lines go down forever, so it's not going to be the absolute lowest point, but it will be a local minimum. Okay, up here, there is nothing else above it, so this one will have to be the absolute maximum. The next one is a local minimum. Again, there's not going to be an absolute minimum because of these arrows that go down. Okay, and then this one here has to be a local maximum. Okay, moving on to the next page. So this one is kind of more just like a visual thing. So it's talking about boundedness of graphs. So you can have an upper bound, lower bound, a combination of both, or neither. Okay, so here you see we have an example of something that is bounded above but not bounded below. Okay, so it's bounded above, meaning it's not going to go all the way up there, but it is going down, and it's missing the arrows, but it is going down. That looks ugly. Okay, this one is bounded both above and below, so the graph will only exist within the bounds. This one is bounded below, and it does go up to infinity, so it's not bounded above. And then the other one is opposite. It's not bounded below because it goes down to negative infinity, but you can see that it's bounded above, meaning it's not going to go higher than that bound. Okay, this next example is not bounded above or below. It goes up and down forever. And the next one goes up forever, but it is bounded below at the bottom. So those are just some examples of boundedness. But yes, we can go on to the next page now. So this page talks about symmetry. We're going to be talking about even versus odd functions, and we'll start with even. So when you have symmetry with respect to the y-axis, that's going to give you an even function. Okay, this is even, and graphically what that means is that you can reflect it across the y-axis and they'll be the same on both sides. Okay, so reflects across y-axis, graph is the same on the left and the right. Okay, so you can see we have our first example, f of x equals x squared, and these can be represented graphically, numerically, and algebraically, and I'm going to show you how to do all three of them. Okay, so if it reflects across the y-axis, you can grab your paper and fold it along this line, and you'll see that these 2 points will touch. So if when you fold your paper, they overlap, then that will be an even function. Now, don't be confused because sometimes they'll try to trick you and give you a perfectly symmetrical graph, but it's like somewhere over here. So if it doesn't happen on the y-axis and it happens somewhere else, yes, it is symmetric, but no, it is not even. Okay, so it has to be symmetric with the y-axis. Okay, now you can see we have 2 points here. You're always going to have this be the same. For the x values, they're always going to be opposite. That looks ugly. Hold on. And what I mean by opposite is that one of them will be positive and the other one will be negative. So you have opposite signs for the x values. Opposite x values. One is positive, one is negative. However, for the y values, they're going to be the same. So they're either both positive or they're either both negative. Okay, so you have the same y values. So that's how you can tell on a graph. Numerically, you can see the same thing. So from here to here, we have, I'm really struggling here, making these little lines. From here to here, we have opposite x values. So we start with negative 1, 2, 3, and then we have positive 1, 2, 3. So the sign changes, they're opposite. So I'm going to put opposite x values. But on the other side, you can see we have the same values. So we got positive 149 and positive 149. So the y values didn't change, they remained the same. So same y value. So when that happens, you'll be able to tell if it's even. Okay, now algebraically, what you're going to do is basically plug in a negative x for every positive x that you currently have, and then you're going to solve. So the rule is if you plug in negative x, you should end up with the same x value. Sorry, with the same f of x value. Remember that f of x is the same thing as y. Okay, so let me give you an example. Let's see, example. If I were to plug in f of, let me see, negative 3 versus positive 3. Okay, when you find f of 3 on the table, you have a positive 9. If you plug in a negative 3 on the table, you still have positive 9. So regardless of your x being positive or negative, you end up with the same y value, okay? Remember that y is the same thing as f of x. So again, regardless of whether you plug in a negative x or a positive x, your values will be the same, right? 9 and 9 are equal to each other. These are equal to each other regardless if it's negative x or positive x. When that happens, then that's when you know that it's an even function. Okay, so let me show you what that would look like when you're doing it by hand. Okay, so right here we have the original function f of x equals x squared. So I'm going to come down to the bottom and write the original function in orange, which is f of x equals x squared. Okay, what you're going to do is plug in a negative x for every x that you see. So instead of positive x, negative x. And always put your negative x in its own set of parentheses. Don't just leave it, like with a negative anywhere. It has to be enclosed in parentheses. Okay? And then all you're going to do is simplify. So when I simplify negative x times negative x, well, that's what negative x squared means, right? You're basically multiplying that same value by itself 2 times. So negative x squared is negative x times negative x. Okay, what is negative times a negative? A positive. And what is x times x? X squared. Okay, so you can see that f of x is equal to x squared, and f of negative x is also equal to x squared. So regardless of if I plugged in a positive x or a negative x, in the end, I got the same thing. So when you simplify and it ends up being the same as the original function, that's when you know that it's even. So I'm going to make a note, same as the original. And here's a little mathematical shorthand for you. Instead of writing therefore, mathematicians use these 3 little symbols in a diamond or a pyramid formation. So same as original, therefore it is even. Okay, so essentially what happened was that f of positive x was equal to f of negative x. Okay, because both f of x and f of negative x are equal to x squared, right? They are literally the same thing. They are both x squared, regardless if x was positive or negative. Okay, moving on to odd. So an odd function is when you have symmetry with respect to the origin. So if you have symmetry with respect to the origin, you get an odd function. And graphically, what that looks like is you can rotate the graph 180 degrees. 180 degrees is upside down. If you turn your paper upside down, the graph is the same right side up and upside down. Okay, so here's our first example of odd. F of x equals x cubed. So graphically, if you were to grab your paper right now and turn it upside down, you would see that they are the same upside down. Okay, we have a point here, positive x comma y. Okay, x, y. And this one is negative x, negative y. They're just not written there, so I'm writing them now. Okay, and like I said earlier, your x values will always be opposite. Let me do it another way. This versus this one. Okay, so these two are opposite x. Now the difference between even and odd is that your y values are also going to be opposite. So notice that it changed from negative y to positive y. Okay, so both the x's and the y's switched signs, making them opposite signs from each other. Okay, numerically on the table, you see the same thing again. Negative 1, 2, and 3 became positive 1, 2, and 3. So we have opposite x values. And the same thing for the y values. We have negative 1, 8, and 27 and positive 1, 8, and 27. So the y values are also opposite. Okay, an easy way you can remember this is that they all start with O. Okay, odd, origin, opposite, x, opposite, y. O, 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 O. Okay, O, 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 O. The other ones are all different. Okay, so if you have a problem where you have an opposite x and an opposite y, O, 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 you need to know that it's odd. Okay, now algebraically, when you plug in a negative x, you're going to get the same y value back, except that it's going to be negative. Okay, so you're going to have negative f of x. So let me give you an example of that. So we can plug in the same f of 3 versus positive 3. F of negative 3 versus positive 3. Okay, f of 3 on the table, you can see it gives you a positive 27. But f of negative 3 gives you a negative 27. Okay, so notice that if this negative sign was not there, these y values would be equal to each other. They would both be 27, regardless if 3 or negative 3 were placed into x. Okay, but when we put a negative 3, we got a negative y value. So f of negative x is equal to f of x, but with a negative in the front, right? So this became 27 versus negative 27. It's the same thing, just with a negative in the front. Okay, and when that happens, that will be an odd function. So let me show you again by plugging in negative x into the original, which is x cubed. So the original was f of x equals x cubed. What I'm going to do is replace every x with a negative x, and everything else about the function stays the same. Just that every time there was an x, I'm now putting in a negative x. Okay, and I'm going to simplify this. Negative x cubed means that I'm writing x, or I'm multiplying negative x by itself 3 times, right? Negative x times negative x times negative x. Okay, a negative times a negative makes a positive. Bring down the negative. A positive times a negative makes a negative. So this will end up being negative. And then x times x times x is x cubed. Okay, so we have negative x cubed as our simplified answer. A trick I can give you to remember your negatives or positives: if your power is even. So for example, on this one, the power was even. If the power is an even number, you're always going to have two pairs that will make a positive. So it'll always be positive if it's an even power. Okay, so if the power is 2, 4, 6, 8, 10, 12, etc., it'll always be positive. However, if your power is an odd number, so 1, 3, 5, 7, 9, etc., you will always have a pair, but then there'll always be a random negative floating around that will make the whole thing negative. And that's why your answer will always be negative. Okay, so remember that, because if I give you a problem that's negative x to the power of 27, I don't want you there writing negative x times negative x times negative x times. We don't have time for that. Okay, even number, positive value. Odd number, negative value. Okay, so notice that this one, when we plugged in f of negative x versus f of positive x, we got x cubed here, and this one was exactly the same, x cubed, they're the same, right? X cubed, except this one has a negative in the front. And that matches with the rule that we had talked about in the first place, where we had said that f of x was the same thing as a negative f of x. Okay, so they're the same. F of x is x cubed, and then we had a negative x cubed when we plugged in a negative x. Okay, so that's all that's saying. You get back the same thing, but with a negative in the front. Okay, so I'm going to say that this one was the opposite as the original. By opposite, I mean the opposite sign, right? We started with negative and we ended up, we started with positive, we ended up with negative. So it's the opposite sign as the original. Therefore, it's odd. Okay. Oh, sorry. This needed to be, I messed up. Oh, big eraser, not that one. So f of negative x. Let me just rewrite the whole thing. Okay, so f of negative x was the same thing as a negative in front of the original f of x. Okay, so when I plugged in f of negative x, I got negative x cubed, and the original was x cubed, but I'm putting a negative in the front of it. Okay, so f of negative x is equal to negative f of x. So now let's put these rules and stuff to use. Okay, so let's start with example A. Everywhere you see an x, you're going to replace it with a negative x. So instead of f of positive x, we're going to have negative x. And instead of x squared, it's going to be negative x squared minus 3. Okay, you simplify after that. Negative x squared is positive x squared. And you bring down the minus 3 that we didn't touch. I only want you to simplify from the equal sign to the right. This, leave it alone. You're just going to bring it down. All you're doing is simplifying. Okay, when you're done simplifying, you're going to compare. Is this the same as this? You can see that it's exactly the same. So when I plugged in a negative x, it was equal to the original f of x. Okay, so f of negative x was x squared minus 3, and f of x was x squared minus 3. So they're the same exact function. So I can say, therefore, it is even. Okay, let's try another one. So here I have g of x. Again, every x that I see, I'm going to replace it with a negative x. So g of negative x is equal to negative x squared minus 2 times negative x minus 2. And make sure you're putting all of your negative x's in their own set of parentheses. Okay, negative x squared is positive x squared. Negative 2 times negative x is positive 2x, and then bring down your minus 2. Okay, so let's compare. Are these the same as this? It's almost the same, except this minus became a positive. So for this one difference, it is not going to be even. Okay, so g of negative x does not equal the original function of g of x. Okay, so I know it's not going to be even. So now let's see if it's odd. The way to see if it's odd is you're going to factor out a negative. Okay, so negative, let me move this down actually so we can see this better. So if you factor a negative out, all you're doing is figuring out what this would be equal to if I take a negative out. So a negative times what is positive x squared? Well, I know two negatives make a positive, so it has to be negative x squared. A negative times what would be positive 2x. Okay, it has to be negative 2x because only two negatives make a positive. And then a negative times what is negative 2? It has to be a positive 2 right there. So you end up with negative x squared minus 2x plus 2. Now, ignore this negative for now. All I want you to do is grab the stuff in the parentheses and compare it to the original. Are they the same? And you can see that they are not the same. So let me bring this back. So we tried testing to see if it was even. It failed. We tried to test to see if it was odd by taking a negative out of it, and it also failed. So yes, you can have a case where it is neither even or odd, and this is neither. Okay, so again, you simplify it. If it's the same, even. If it's not the same, try to factor out a negative, and if it's still not the same, then it's neither. Okay, let's try a third example. I'm going to replace the negatives. Sorry, I'm going to replace the x's with negative x. Everywhere I see x, so that's negative x cubed in the numerator and 4 minus negative x squared in the denominator. Okay, negative x cubed will be negative x cubed, and at the bottom we have 4 minus, and then negative x squared is positive x squared. Okay, so let's compare. Are these two the same? No, they are not. This one is negative, this one is positive, so it's not even. So what we're going to do is try to factor out a negative to see if it is, odd. Okay, now the thing with taking fractions, with taking negatives out of fractions, is that you can only take a negative out of only the numerator or only the denominator, but never both. So let me show you what happens. If I want you to factor a negative out of negative 7/3, you could do negative 7/3, right? Or it could be the same thing if instead I had 7 over negative 3. So it doesn't really matter where the negative goes, in the bottom, in the top, or on the outside, but these are all equal to each other, okay? Now, if I had given you the same fraction, and so let me do it down here, and you had tried to take out a negative, some kids, what they want to do is take it out of both, okay? So if you take a negative out of negative 7, you're stuck with positive 7, and if you take a negative out of 3, positive 3, you have negative 3. So this is what some kids try to do, is take the negative out of both the numerator and the denominator. What they're not realizing is that these two negatives ultimately make a positive, right? A negative divided by a negative is a positive. So now these are not equal to each other. Negative 7/3 is not equal to positive 7/3. Okay, so for that reason, you're either only going to take it out from the bottom or the top, and you just put it on the outside, but you don't want to take it out of both the numerator and the denominator. Okay, so back to our problem. The numerator is negative x third, so I think I'm just going to take the negative out of the numerator. So in the numerator, I'm going to take the negative outside and leave the positive x cubed on the inside. And then because I already factored out a negative, I'm going to leave the denominator exactly the same. Okay, and then I want you to analyze inside the parentheses, is it the same? And yes, it is the same after we factor out the negative. Okay, so after you factor out the negative, after you plug in negative x and you take the negative out, they ended up being the same function as what you started with, except that it was negative. Okay, so for that reason, this function is odd. Okay, let's do some more examples. Okay, so at the top, so this one is labeled end behavior and asymptote. So we've already talked about vertical asymptotes. Now let's talk about horizontal asymptotes. Okay, so this is going to be for horizontal asymptotes. So there are 3 cases, and they sound kind of funny, but they're going to be acronyms that are going to help you really remember where the horizontal asymptotes are. Okay, so the acronyms are BOBO, Boden, and EATS DC. Okay, so BOBO stands for big round bottom. Y equals 0. Okay, big round bottom 0. Big round bottom 0. Bottom stands for big round top. None. Big round top none. Each DC stands for exponents are the same. The DC stands for divide coefficients. Okay, so those are going to be the acronyms, and on all of these you're going to be looking at the exponents. Look at exponents. Okay, so the exponent is bigger on top is BOBO. Sorry, if it's bigger on top is bottom, if it's bigger on bottom is BOBO, and if the exponents are the same, you're going to divide the coefficients. So let's do figure out the horizontal asymptote on all 4 of these examples, and then we'll proceed to figuring out whether they're even or odd. Okay, so if a variable doesn't have an exponent, it'll have an exponent of 1. Okay, so now let's compare these two. So you can see that the exponent of 2 is bigger on the bottom, so it's going to be BOBO. So down here I'm going to write the horizontal asymptote is at y equals 0. And I'm going to draw a horizontal asymptote at y equals 0. Okay. Moving on to the next one, I'm going to compare only the exponents. Okay, the power of 2 is the same on the top and on the bottom, so this one will be a case of each DC. Okay, so the horizontal asymptote. So if the exponents are the same, you have to divide the coefficients. The coefficient is a number in front of the variable. In front of the numerator variable, we have 3. In front of the other one, an imaginary 1. So if you divide that, that's 3 divided by 1. So y equals 3 divided by 1, which simplifies to 3. Okay, so there's a horizontal asymptote at y equals 3. Okay, let's try the next one. So looking only at the highest exponents. So you can see that the power of 3 is bigger than the exponent of 2, so it's bigger on top. So there is no horizontal asymptote. When you don't have a horizontal asymptote, you have a slant asymptote, and I'm going to teach you how to find that in a few class periods. Okay, let's compare the last one. We got x to the power of 4 versus x squared. So the power of 4 is bigger on the top, so this one also has no horizontal asymptote. Okay, so now what I want to do is graph all of these, and we're going to be creating tables for them. And don't make them too big because we're not going to have that much space. We're going to graph all of these on the calculator and find some coordinate points to sketch our graph. Okay, so we're going to start on the calculator with example 1, which is 3x. And at the bottom we have x squared plus 1, enter. And you can see that it looks like this. And then you pull up the table by doing menu table split screen, or you can do Control T. And so I'm just going to pick some of these points, and I'm going to, for all of them, I'll just do -2 to +2 to make it simple. Okay, so at -2, we have -1.2, -1.5, 0, +1.5, and 1.2. Okay, and then I'm not gonna spend time trying to make it perfect. I'm just going to sketch it as best as I can, and it's gonna look kind of wonky, but it's okay because you already know what the graph looks like. So it looks kind of something like this. That looks really bad, but it's okay. Okay, now for the sake of time, I have already plotted these, so I'm just gonna fill in the tables. But if you have a calculator, you can also do this on Desmos. If you're at home on desmos.com, and you can pull up the table. 2.4, 1.5, 0, 1.5, 2.4. I've also realized that some of you guys don't know how to pull the table up on Desmos, so I guess I can show you how to do that. So for the second example, you start with putting the division 3x squared over x squared plus 1. And this graph looks like this. Now to pull up the table, you're going to press on the settings, like little wheel thing up here. Click on that. And then you have some options. The first one is a table. You click on that and you get the points that I just put on the thing. And you can change the value. So if you want to find when x is like -10, you can just change it and it'll populate the y value for you. So I just know some of you guys don't know how to do that. So that's there for when you're at home trying to do your homework. The next one, oh, let me graph it. So that graph looked something like this. These are very rough sketches, by the way. Okay, the orange one, again from -2 to +2. Those are -4.8, -1.5, 0, 1.5, and 4.8. And that kind of makes a cubic graph. Okay, like this. And the green one. Now, you guys will probably have time to make your graphs better. I'm kind of rushing because, as you can see, my iPad is going to die soon. So I want to make sure I finish the video before it dies. So take your time to sketch these properly. I'm just trying to do them all rushed. Sorry. I should have charged my iPad. All right, so now I want to observe whether they're even or odd. Okay, so if you remember, if you look at the x value and the y values, if they're opposite or the same, that's how you're going to tell. So here we have negative versus positive. So here they switched. So if your y values switch, remember O, 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 this is going to be odd. Okay. On the next one, when you look at the y values, they are all positive. So since they're all positive, they remain the same. And if your y values stay the same, that's how you know it's even. Okay, on the orange, you can see they also changed signs. They started negative and then now they are positive. So if it's opposite, O, 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 it'll be odd. And then for the green one, they are all positive, so they stayed the same. So if the y values stay the same, then it's even. Okay, and you can also tell graphically. So remember, if you can reflect it across the y-axis and they touch, so these two, where they're even, you can reflect it across the y-axis and they'll be the same on the left and the right. And these that are odd, if you were to turn them upside down, they would be the same graph. Okay, so now we've confirmed graphically and numerically that they're even and odd. Now we're going to try to do these all algebraically. Okay, so the original functions are up here in the black ink at the top. So when I say look at the original, is it the same? I'm asking you to look up here on the top. Okay, so I'm going to start by replacing the x's in the originals with a negative x. So on all of these, we're going to be doing negative x. Okay, and make sure your negative x's are in parentheses. You see? Oh, I have low power mode on this thing. Okay, whatever. Negative x squared plus 1. And then you simplify. 3 times negative x is negative 3x. Negative x squared is positive x squared plus 1. It's not the same, so what I'm going to try to do after that is take a negative out. And remember, when you take a negative out of a fraction, you only do it to the top or the bottom, never both. I'm only going to take it out of the top, and I'm going to leave the bottom the same. Now, observing just this bottom one, you can see that it is the same as what we started with at the top. So I'm going to write the conclusion that when I plugged in a negative x, I got the same thing as f of x. The same thing as what I started with, but with a negative in the front. Okay, so for that reason, another piece of evidence that this function is odd. Let's try it again with the second one. Okay, so everywhere there was an x in the original, I'm going to plug in a negative x. Okay, so 3 times negative x squared over negative x squared plus 1. Okay, negative x squared is positive x squared, so that's just going to be 3x squared on the top, x squared at the bottom plus 1. And if you compare it, they are the same as the one at the top. So when I plugged in a negative x, it was equal to the original f of x at the top of the screen. And when that happens, it is even. Okay, let's try an odd one. So f of negative x. So when there is a when there's an x, replace it with a negative x and close it in parentheses. Okay, so what is negative x cubed? Remember, if your power is an odd number, the value will stay negative. So that'll be negative x cubed times positive 3, which is negative 3x cubed. If your power is even, like the denominator, which is squared, it'll be positive. Okay, and that's not the same, it's not the exact same, but let's see if I can take a negative out. If I factor out a negative, what will I have? Okay, so I'm going to choose to factor the negative from the numerator, and I'm going to leave the denominator alone. Now, if I were to go back up and compare it, they would be exactly the same except with a negative, right? So when I plug a negative in, I get the same f of x, but with a negative in the front, and that's the definition of an odd function. Okay, let's try the last one. So again, plug in a negative x. Everywhere you see an x. Oops. Okay, so again, when you have an even number, 2, 4, 6, 8, 10, the sign will be positive. Okay, so we have a positive 3x to the power of 4, positive x squared plus 1. Notice that it is the exact same thing that we started with, so we can conclude that when we plug in a negative x, it was the same as the original f of x that we started with at the beginning. So this one is even. Okay, so now finally I can zoom out and show you we have found the symmetry of these graphs, both graphically, numerically, and algebraically, and all the way through we got the same exact answer. Now, a lot of the times, I will ask you more often than not to find these answers algebraically. You can confirm your answers using the calculator, graph, and table, but if I ask you to do it algebraically, I do expect to see your work by hand like this. Okay, I hope that this was helpful, and I hope that you understand. And if you have any questions, just let me know, and I'll see you in the next video. Goodbye.